Hello, everybody. It's night 2 of SDEV 140. Went over policies and kind of jumped into an example. So we would be doing something the other day. Now we're going to jump in and I guess review the review section, recap what was covered in the previous course, maybe take it a little bit further. So start with an analogy here, just sort of a comparison on what we're doing. Where are the markers? There's markers. Before we jump into the review too much. Programming language is a tool. Let me write that on the board. A programming language is a tool. And what gets done with that tool and how well it's done is up to the programmer. What it does or how well it does it is up to the tool user. That statement generalizes to probably any tool we can think of. The tool is made for a job, but how well it does that job is really up to the tool user. There's some more stuff we'll talk about. An example I like to use for an analogy when talking about just approaching it, thinking about it as a tool, is a hammer. The board is kind of a mess from earlier. It's not erasing very well. Are other people having trouble reading that? And the chat room says it looks a little bit blurry. Maybe I can zoom in a little. Is that better? I'm trying to pull it up big on my screen. Yeah, I think some of it is just the board is messy from earlier. I'll try to write larger and bigger. So all this says, a programming language is a tool. That's what it really is. It's a tool we can use. And like any tool, how well it performs its job is up to the tool user. If we're using a tool we don't know how to use, we're probably not going to do very good work with that. The standard example I like to go with when thinking about tools is a hammer. And if we kind of break down and think about what a hammer really is it's actually a combination of levers. Right? If we have a spot that something can bend around and we can adjust the length across, we call that the fulcrum, the spot that spins around, and we can adjust the pressure on each side of that depending on how long the arms of the lever are and how much pressure is applied. But a hammer is a combination of fulcrums, has 2 pivot spots built into the machine, turn a lot of pressure to redirect forces. There's also some stuff from the arm so that when an arm moves forward, this lever, the handle, spins this other lever, and then that causes a huge increase in force out this side or out this side. And what the tool is really doing,
so I can see the chats.
okay, is usually one side of it's for pushing, one side's for pulling. with a hammer. Normally, we would be doing that quick enough that we would use the words hit and pry, but we can push things slowly with a hammer. But it's a couple levers that redirect force. But when you put that in the hands of
Okay. So,
Okay, yeah. Sorry about that. So it's a tool, lots of people can use it, but different things are gonna happen with that tool, right? If you hand that tool to a 3-year-old, something's probably gonna get broken. If you hand that same tool to a master carpenter, they're probably gonna be able to make some really nice stuff with it. So how well it's used depends on who's using it. And the purpose of a hammer is multiple levers to redirect forces to push and pull stuff. Normally fast enough to say hit and pry, but we can push slowly with a hammer. That works too. But is that the only way a hammer can be used? That's something that a lot of people think when they're first starting into programming. We see the tool that we have to work with, and people expect it to be like a factory assembly line thing. Like once you see a selection structure, some people come in thinking, once they've seen how to make a selection structure, they're going to be doing that for every single selection structure to be exactly the same, and that's not the case. Every single one we do is different. And the reason is what we're doing, the job this tool is for, is problem solving. And problem solving is very non-repetitive. Every problem is a new problem. The problems we've solved before might help with the new one, but they might not. It might seem similar, but it's entirely different. With problem solving, every problem is a new problem. So what we look at in the class a lot is just the tool and some simplified examples that fit in our time constraints. That's the biggest thing about learning this in the classroom, is we are under very, very tight time constraints. We have, well, if we did the full amount from 6 to 8:50, I'll just say 3 hours, 2 nights a week, so 6 hours a week for eight weeks. Sounds like a lot of hours, but we'll barely scratch the surface of it. And also, anything we do has to fit in those time constraints. So everything you will see in a classroom is designed to fit in those time constraints. And for a note about software development in general, that is one that catches people by surprise when they graduate. So I like to always try to throw out warnings of that starting early. Everything you will see in the classroom has been specifically selected and chosen to fit in the classroom. When you all submit your project proposals for the software that you want to make to show off your skills and the culmination of this course, the most likely reason that I will reject something is that it will be too big for our time constraints. I guess it's possible that somebody might want to do something really, really small, but usually when people turn in project proposals, they want to do something big. So the problem we encounter is that I look at the proposal and I'm like, yeah, there's no way this is going to be done in 8 weeks. And everything we'll see in the classroom is specifically selected and kind of filtered down to fit in our time constraints. There'll be some problems that you struggle on. Hopefully you're struggling on them. If it's easy, that means you're below your skill level. So you want to struggle a little and improve along the way, which can be frustrating. It does get very frustrating, and the in-class examples probably aren't helpful. I prepare ahead of time. What happens when you all write your programs, right? There's all kinds of typos, and sometimes the logic needs adjusted afterwards and all that stuff. That happens to everybody. Even after decades, that still happens. But we're under tight time constraints in the classroom, so I prepare ahead of time. So the in-class examples we'll see look overly simplified. Same thing for the textbook and other tutorials you might see. Those are already edited and polished off. You're seeing the finished version. And the process to get there is what you're all probably already experiencing. Lots of typos, little mistakes in the logic. So at least once in every software development class, I do like to do a unprepared lecture. Come in and just make one up. Don't even pick a topic until after class has started. That way y'all can see that the process is what you're used to and all those little mistakes happen. And the reason the class examples seem to go through without all those mistakes is because I already made those before we got here. That way I don't waste the class time. So there will be at least one unprepared example every time. And the last thing about the time constraints is the one that catches people off guard. Because in the classroom, even for the school in total, right? There's a 2-year degree, it's community college, so a 2-year degree. Anything we do has to fit in that time constraints. In the classroom, everything has to be a lot shorter than that, has to fit in that course. But the world at large has moved beyond those small things into bigger problems. So that catches a lot of people off guard. They do really well with the small things that are specifically chosen that you could figure them out in our time constraints. Even if they're a bit of a struggle, they'll be able to figure them out in a couple days or a couple weeks at most. But software development at large, after academia, it catches people off guard because the field has already moved to much bigger problems. So right at graduation, there's that transition where it's not just a little step up. You'll be transitioning from the stuff that fits in the classroom to things that a team of 15 people will have to think and discuss and debate and spend 9 months trying to figure out how to solve the problem. So there's that huge leap at the end. Because of the time constraints, there's not really much we can do about it because we have to see so much in the classroom. So in the long run, be prepared for that. The world at large has already moved beyond the small things like we'll see in the classroom. And after you graduate, you'll be into really big problems. You might get hired somewhere and be put on a team where they've already been working on something for 3 or 4 months and don't have any notes even worth keeping from what they've got in their algorithms at this point. So the problems get very, very large after graduating. Just want to keep that in mind. And what we have is a tool. There's lots and lots of ways to use the tool. And that's what we want to get practice with. That's why we have lots of small assignments to practice different ways using the same tools so that we can put them together because it's a tool for problem solving. I'm gonna go ahead and erase this. That's okay. It's been up here for a minute, just a quick note, and it was kind of blurry. Let me see if I can erase it better so that the next ones aren't as blurry. Because the next note is one of the most important things for problem solving. It's what tools we actually have when we say programming language. The really good markers that draw really dark are nice for how they show up on the video, but they're kind of hard to erase. Whatever one I was using this afternoon. So like I just said, software development is about problem solving. Excuse me. And it just so happens that in order to solve problems, there's a short list of tools that we need. You may have encountered this before. They're called the 4 constructs. And in order to solve a problem, not just a computer problem, any problem whatsoever. There's only 4 types of tools that we need to put together a solution for any problem. There's big fancy mathematical proofs about this and everything. So the first one is a sequential tool. I'll write it that way. Something to define the sequence or the order that things are going to happen in. We need a tool to say what order things are going to go in. For programming, that one's pretty easy. That's the order we write our lines of code in, or the order we call our code in, the order we run each instruction in. And we need some sort of tool to make selections, make choices along the way, have decisions, various alternatives. The third one is reiteration. And I'm going to be careful about using that word in lecture. So reiteration and repetition. In general English, we can use those interchangeably, right? There's definitely some synonyms, but for our lecture, our class here, I will keep coming back to the 4 constructs over and over and over again, because that's really what we're studying, the tools to solve problems. I'm going to use reiteration and repetition differently. So repetition is an exact duplicate, and reiteration I will use for repetition with variance. For example, mowing grass. Yeah, get out a push mower, you need to mow the grass. So if you stand behind the mower, start it up and all that, and push it down across the yard to mow a strip, get some of it mowed. Repetition would be backing up to the starting point and pushing that mower again, mow the same strip over and over and over again. If we do that, we're never going to get our yard mowed, right? We're only going to get that one strip mowed no matter how many times we go over it. I'm going to use reiteration for repetition with variance. So like mowing a yard, we're going to push the mower across the yard, get a strip mowed, but then we want to, I'll pass the camera. Then we want to turn around and move over so that we mow the next strip. And then turn around and move over. So we're kind of repeating, there's that repetition, we're mowing a strip, but it varies each time we move over and turn around so that we're not mowing the same strip. That's how I'm going to use the reiteration versus repetition. When I say repetition, that means an exact copy. Because sometimes that is what we want, right? Like an animated logo seems like a good example. We have a little animation, like our company logo is a dancing clown. We want that clown to sit there and do that same dance over and over again the exact same way for as long as somebody's on our website or wherever they see our logo at. That would be repetition, the exact same thing over and over again. So I will be using those words differently. And the fourth tool is something that can handle invocation. We need to invoke outside resources, use outside resources. There's different words that could go in there. I'm going to use these 4. So sequence, select, reiterate, and invoke. And I'll keep using those over and over and over again this semester because that's the types of tools we're studying. Not just for, and this is the tools we need to solve any problem. That most famous one, world peace. The solution will only involve these 4 types of tools. Just on that particular one, nobody's figured out the right order or the right choices to make. The right choices to make and what order to put them in to solve that problem, famous one. But small problems. You're sitting around watching TV with your friends. a commercial break comes up and you jump up and run to the kitchen to grab everybody a drink. That's a problem that needs solved. So there's an order. Get to the kitchen, grab some glasses, probably one at a time, right? Grab a glass out of the cabinet. Go to the go over to the freezer, grab some ice cubes. Put ice cubes. Maybe some of your friends want ice cubes in their drinks. Some of them don't want ice cubes. So you have to choose which cups get ice cubes in them. Then grab, I don't know, maybe soda. Maybe there's a good variety. Some people want Sprite. Somebody else wants Diet Pepsi. Somebody else just wants like sweet tea. And you have to make those choices along the way. And then the reiterating, as far as you're still just filling up a cup with, or grabbing a cup from the cabinet, filling it up with ice or without ice and pouring a beverage in it. So those selection tools. And then invocation, in that case, this example has a good invocation. While you're doing that, one of your friends from the living room changes their mind. Because at first, maybe they said they wanted water. Like trying to go on a diet or something, so they asked you to bring a cup of water. And then as they thought about it, they're like, forget that, go back to the diet tomorrow. So they holler in from the other room that they want Coca-Cola instead of water. So then you have to jump out of your sequence, make the adjustments to fill a glass with Coke instead of water, and then back into your sequence. That's what that fourth tool is. A way to leave our sequence and come back to it. Anything we call a programming language would have all four of these tools. And by the late 1950s, a programming language finally invented. 1957, a programming language was invented that finally had all of the tools included. We didn't have to build new ones. So that's what we're really studying, the tools to solve problems. And we have lots and lots of different problems that might need solved. Lots of unique ones. And we're just going to have a computer help us solve the problem. So these are the tools we're studying. Not necessarily the tool of the computer. The people getting IT support degrees, they're studying the tool computer. We're studying the tools for problem solving, software development, which is something that's going to happen on the machine. So this is a point that we're going to come back to over and over and over again this semester. That's the main, sort of our main concept for the class. What we're looking into, and there's lots of examples. We'll be using Python. This is not the Python course. This is a software development course that uses Python. I've heard that many, many times after this course. People are like, oh yeah, I have the Python course. The first 2 weeks of the Python course, SDEV 220, there's a whole bunch of stuff undoing things learned in this course because of how we use Python here. We generalize a lot of things and step away from the way we would normally do it in Python because it translates to most of our programming languages in a more generalized sense. We overgeneralize Python here, but we still learn a whole lot about it. We'll get quite familiar with it and a good start. But what we're really studying is problem solving. And then the next class is the 200 level class is the language specifically. So we're going to do this on computers. So we need to do some review stuff and get into what computers are really doing. Go through this quick, the review from the SDEV 120 class. Because some of y'all might have just taken that in the last 8 weeks, and some of y'all might have, it might have been a couple years since you took that course. So just a quick review on it. I guess a definition, I'll start with a definition. I'm going to say my definition. This is something you might want to think about. There's what you would go to the textbook and, or go to the dictionary, open up a dictionary and read the definition of computer. That's one thing, but how do you define a computer? If you met somebody that never used a computer, maybe they're from somebody grew up in an Amish community or one of those Mormon communities that shuns electricity, that shuns technology. Somebody from one of those cultures grows up and decides they don't want to stay in that culture, so they can live in our world. What would you tell them a computer is? You probably wouldn't use the definition written in the dictionary, right? So my definition of a computer, and yeah, kind of think about what you think what it means to you or how you would define it, is it is a machine that can detect and react to changes of state, changes in state, or of state, which one would be grammatically correct? Machine that can detect and react to changes in state. Maybe I should have said of state. That's how I define a computer. What exactly does that mean? What is the change of state? So right now, my laptop is sitting here, sitting here on this table, nothing's changing. Well, there's video playing, I'm gonna ignore the video, but none of the keys are being pressed. All of the keys on the keyboard are in the unpressed state. So if I come over here and push the J key, the computer detected that the state of that key had changed. And it reacted to the change, that change in state. Now I'll come over here and change the state of the enter key, and you can see what I typed there. Y'all know what happens when you push the J key down. But the computer detected that the state of that key had changed, and it knew how to react to that change of state. While my cursor was in, while the focus was in the chat room here on Ivy Line. Everybody's familiar with that, but that's what machines do across the board. And what we are doing to detect it, I guess I could add another word here. It can detect, identify, might as well put this in here, and react to a change of state. So all three of them. Because that time I typed the J key, but if I come over here and hold down, press the D key, and then the enter key, something different happened. So not only could it detect it, it can also identify what state is changing. And then it reacts to it. And there's lots of different reactions, right? I chose D key the second time because those people in the afternoon class, when we pushed the D key this afternoon, it was moving an image across the screen for the game development class. So the reaction was something entirely different. That's the part we're looking at in this course. As software developers, we define what the reaction should be for a given change of state. For developers, we define the reaction for a given change of state. That's the most generalized way I've been able to think of to write out that thing. That green marker is not very dark. But that's the part we're at. The hardware detects and identifies it, we're the ones that tell it what its reaction needs to be after making that identification. And we will then apply that to make it useful. We'll apply it to problem-solving methodologies so that useful things happen. Unlike what's currently in the chat room where I pushed just held those keys down for a minute and hit enter. That's not useful. That's not necessarily solving a problem. We want to do this in order to accomplish a specific goal, because there's a lot of computers can do this very, very quickly. So it comes in useful in the problem solving, with problem solving stuff. So that's my definition of what a computer is. Realistically, the state is just a voltage rising above or dropping below a threshold. Move this over and all right, over in this section. So if we plotted it like math class, normally our X and Y axis, but since going for something specific, we don't have to use those generic terms. We can think about time. As time moves forward, the voltage, which is the potential of electricity to do something. Voltage is a potential energy. A good example of it, it would be like a flower pot up on a windowsill. So like on some big tall building up on a window balcony, you might have a flower pot sitting there. And it's way up in the air. That flower pot's not falling, right? It's just sitting there stationary. But it has potential to fall because it's way up, several stories up a building. So if there was a little cat here, little cat could come along, bump up against that flower pot, and then it will be falling. But when it's just sitting on the shelf there, it just has potential to fall. It could happen. That's what voltage is. Voltage is the potential for electricity to flow. Once it's actually flowing, it's going too quick for us to do anything. The flow of electricity is current. And at that point, it's going way too quick for us to deal with. So we adjust when it's nice and slow in the potential. Like moving the flower pot back and forth on the seal, we can change that potential to flow. If we know the cat's moving close to it, we can move that flower pot a little away from the edge so the cat's not going to knock it off. Is a sort of an analogy for that. So voltage is the potential for electricity to flow, and that's what we have control over. And normally we just pick a spot. We'll pick some level of voltage, 5 volts, 5.0 volts, 3.3 volts, 1.2 volts. Those are going to be the most common ones we work with as programmers. And if we need to get to higher voltages, we would use one of those to turn on a bigger switch, and then that bigger, and then full-blown electricians handle the other side of the bigger switches. So usually programmers deal with are down in this level. Most of our machines are using 1.2 volts. Sometimes if we want to do more than just type and show graphics, we need to bump that up to 3.3 or 5 volts so we can do a little bit more. But if we need to get really big, like turn it on and off a power plant, we would just use one of these sizes to turn on something bigger. But we just pick that line for the particular machine, and then our voltage is either going to be above it or below it as time progresses. 1, 2, 3, 4, 5, 6. I'll make like 6 marks there. So maybe the voltage starts down below, and it's electricity, so it's going to be really wiry, right? Bouncing all over the place. Eventually it's going to go up here, come back down, and maybe go up here. And then depending on what side of that threshold it's on, we're gonna define that as either being on or off. So here I'll just say 1.2 volts, that's what most of our computers are running. If we're below 1.2 volts, that's not enough to turn anything on. I guess you think of the threshold as this is enough power to turn the switch on. We can push our button like a button on a flashlight. If there's not enough power left in the batteries, we'll push the button, but it's not going to come on. We don't have enough voltage. So when we're down here, our voltage is on the low side for those first couple ticks of our clock. And the third one, it looks like we jump above that threshold and then back down below it. So L for low and H for high, whether we're above or below that threshold. Then it looks like we go above it. What about this one? The way I drew that, is that, how do we count that one?
That's below.
It's below. But looking at the graph there, is that supposed to be below? Because our other below stuff was way down here. So this is like our off state. Our on state's way up here. That one just barely went below the threshold. Little issues like that happen. That's the little errors that will occur. Questions that arise, we don't really need an answer. I'm going to write L because it is below it. That is definitely where the electricity is at in that graph I drew. But from the way I drew that graph, is it supposed to be an L there? Or whatever symbol we want to use. It's really, it's on and off. I'm going to erase the cat picture. But the same thing, we can make those adjustments for what the potential for the electricity is to be is, and then when we actually activate it and the current is flowing, it flows through those potentials. So it stays low, then it jumps high, low, or it's off at first. So we have like off, then we turn it on, turn it off. Where was I? On, off. It's just that graph, kind of the graph I made up there. That's a lot to write. H's and L's are one thing. I guess we could spell those words out, high and low. A lot of different symbols we could use. If we're trying to solve a problem, it's over there on that list. I don't think it's showing up on the camera anymore. Maybe true and false would work. What we really have is binary states. We just have two distinct states. Binary just means two. The word binary does not have to do with computers. Computers just make use of the concept that shows up elsewhere. In our modern world, that seems to have slipped away a little. Some of the things. There was very, very little new knowledge with computers. So any of the terminology we use, any of the math that happens, any of the concepts, all of that stuff predates computers as we know them. The new computers were the combination of things that were already known, some of which had been known for thousands of years. And they're so prevalent in our society, those words have become commonplace, and a lot of people think those words come from computing. But computing didn't really introduce anything new itself. It just applied stuff. But binary is two distinct states with no overlap. Things are one or the other, red or blue, up or down, left or right. We could use all those words. We could say this is blue, red, blue, red, blue. That would mean the same thing. Which actually, instead of the words, I probably could have grabbed the red and blue markers and just mark it that way. And it's not even words. Why not do that? So instead of saying all that off on, we could say blue,
Couple more blues there. And a couple reds there. There's a distinct difference in those colors. We can tell it's definitely one or the other. Maybe those colors would be helpful for whatever problem we're trying to solve. Or true and false, which we could define either way we want. We could say that's true, that's false, true, false, true. Or somebody else might look at that same thing and define it completely opposite. The electricity those symbols are all talking about is exactly the same. All that's changing is the symbol we're using. And we are defining the symbol as we need it. So there's a couple reasons to use a certain symbol. Eventually we'll get to doing math with computers, but electrical engineers use the symbol beyond math. And we're going to write this stuff a lot. So we want some nice, easy symbols to work with. In computers, we do math with it, so it has more meaning when we get there. But electrical engineers uses the symbols beyond. And two of our easiest symbols to write are going to be circles and straight lines, which correspond to the numbers 0 and 1. 0, 1, 0. So we could write it there. But whatever happens, however we notate it, it doesn't really matter. And when we're thinking about this stuff, if whatever problem we're trying to solve requires us to think about this stuff, we're probably going to need to use different representations, depending on the situation. Sometimes true and false work. Sometimes up and down might make more sense. Left and right, front and back, top and bottom, blue and red, black and white. Lots and lots of different binary representations we can use. So you want to keep your mind open for the different ways that can be represented, because different symbols or different terms can help you might make it more useful to solve things. Let's see. Can't drift away from my notes. Yeah, so one key word here, what I drew here with the threshold, and we're above or below that threshold for our on and off states. That's what's called von Neumann architecture. That's what we mostly use. But a couple years ago, there was finally a breakthrough after 80 years of trial and error. There was finally a breakthrough in non-von Neumann architecture, where instead of just that threshold that we're above or below, we can use that entire range of voltages. So everything, all those wiggles up and down of electricity, that entire range instead of just the binary states. So that is something that is advancing quickly and moving forward. It's pretty much still in the scientific research stage, figuring out what it's going to be there. But if you're heading into a computer field now, there's a really good chance you'll see it at some point. There's been non-von Neumann machines around for a while. We usually call that analog computing, but it's full blown computing with the analog voltages. So it's not the step down like what we usually refer to as analog computing. There's finally an advancement in that after many decades of trying, basically 80 years. But in general, it's the binary states. And then we can do things with these. Patterns can show up. In particular, anytime we see this pattern, we can say this means 5. Doesn't matter if we represent it blue, blue, red, blue, red, blue, or 0, 0, 1, 0, 1, 0. We can just kind of set up the reactions in the computer to identify this pattern to mean the number 5, which is the next thing to talk about, reviewing from the previous course. Numerical representation with these things. A very quick pass at it, which I guess I need to erase the board now because I'm going to fill it up quickly. Is it okay if I erase the, well, I'll come back over to this side. I'll erase it a little section at a time. I'll start here. Any questions about that general idea? I see head shaking no here. Does this idea make sense? The identify change of state and react to that change of state. That's what I've come up with as far as the complete generalization of what the machines we're working with deal with. Notice I keep saying machines, not just computers, because IoT is a big deal in the modern world. That's Internet of Things, which is tying all of our stuff that is not computers into our computers. Networking our refrigerator and coffee pot to our computer to get more uses out of the refrigerator and coffee pot because of what the computer can handle. That is a big thing. So that is something you'll see in what we're looking at here applies elsewhere. So the next thing, review, everybody should have seen this before, is numerical representation. You would have seen it in this SDEV 120 class, but to start off with, let's go all the way back to elementary school when you're learning to write numbers. You probably haven't thought about what a number means, right? If I write this, everybody knows what that number means, don't you? And you probably haven't thought about how you know what that number means since elementary school. It's we know what it represents because we have a basis for these symbols that we use to do numerical things. As humans, we base most things on 10 in our society, so we count that on our fingers. Right? We have 10 fingers, so that seems like a good thing to base numbers off of. It's not the only system. Can I turn my camera on here? You've probably heard of the Babylonian base 60 system. Base 60, I guess, that is counting on your fingers as well. A lot of people don't realize that, so I started showing that in class. But instead of just counting our whole finger like we do here as Americans, each one of our fingers has different 3 sections on it. So instead of counting the whole finger, use your thumb and tap on each of those 3 sections, and then you can count to 12 5 times. Like, right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we got to count once. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Then twice. So we can count to 12 5 times. Or like on a clock, we can count to 5 12 times using our fingers. I like to show that in class because counting to 60 on our fingers is something that the Babylonian system that often confuses Americans is also counting on our fingers. Because it sounds so big, but it's just different than what we're used to, and it's that it's on our fingers still. But here in America, we just count the whole finger, so we have 10 fingers. Seems like a good number to base things off of. So that's what all of our numbers are based off of. We organize them into columns, and each column is based off a power of 10. So in this case, there's 4 columns, 1, 2, 3, 4. I'll write 2 extra ones. So our smallest column is 10 to the 0th power. It's just a rule in mathematics that anytime we raise something to a power, y'all remember exponents, like 2 to the exponent of 3, or 2 to the 3rd power, that means 2 times 2 times 2. we're gonna multiply the number by itself that many times. Well, zero is a little bit funny, right? The way I like to think of it is some number raised to the zero power. Well, we don't have zero, otherwise we would have wrote a zero here, not the x. But we don't really have that number we wrote here. So we don't have nothing, but we don't have the don't really have the symbol we're using either. So the middle ground there is we have a one. We have something, our most basic version of something, not nothing. So a rule in mathematics, anytime we have something raised to the zero power, that's a one.
Any number raised to the power of 0 is 1.
Yes. Well, what number we put, if we raise it to the power of zero, it's one. Except zero. That's a special case. Because in this case, we do have zero. That's something called an indeterminate. But any number except zero raised to the zero power is going to be one. And then we just increase our columns. So 10 to the first power, we're going to take a 10 and multiply it by itself one time. So we're not going to change it. Gives us a 10, 10 squared. We have a hundreds column, 10 cubed, 10 to the fourth, 10 to the fifth. And we have a column for each power of 10. And then that's where these numbers come in. So 8, 2, 1, 3, and then zeros before up to where I ran out of room there. So we have 0, 10 to the fifths, which would be 10,000. No, 100,000. No, 0, 100,000s. 0, 10,000s. Looks like we have 3 10 cubed. So 3 times 1,000. Plus we have 1 in our 100 column. 1 times 100. Plus 2 of those 10s. And then 8 of those 1s. And that's where the meaning of that number comes from. I just wanted to write it out because it's probably been a little while since you saw that. We don't really think about it after elementary school, right? We practice that over and over again in kindergarten, first grade, very young elementary school. And then we start taking it for granted until we need to do something different. Like 10's not going to work for us anymore. This is what's written over on this side of the board. We only have 2 things. We don't have 10 things if we're either above or below our threshold. And exactly on our threshold, we would just uniquely identify whether we want to count exactly at that threshold as above or below. We're gonna skip over equal to and only do maybe less than and greater or equal to. So it has to be in one of those 2 states. So 10's not very useful anymore. We need a different number. And there is nothing special about 10. The only thing special about 10 is that we have 10 fingers, so that's a good number for humans to work with. I'll do a different one in real quick on the way to the one we're going to. It's okay if I erase the middle section? I see a head nod here in class. So we can use any base we want. Let's go with 6. Let's look at something in base 6. Just to show there's nothing special about that. Well, one thing in base 10, which when we're changing it, we usually write a little subscript at the bottom to indicate what base we're in. We need 10 symbols to represent our numbers. There's 10 different things that could go there. And 0 is one of them, so our symbols are 0 to 9. So if we're in base 6, we need 6 symbols to represent any number we want to talk about. So we probably still want 0. So our symbols will be 0 through 5. That gives us 6 symbols to work with. And I'll just make up a number. 3, 5, 2, 1 in base 6. What does that represent? Because when we write it down, it's just a representation of something. So just like we did here, we'll put each thing in a column. Only our columns will be the powers of 6 instead of 10. So 6 to the 0, again, anything to the 0 power is 1. 6 to the first power is 6. 6 squared is 36. What else is there? 6. And then, the 36 times 6 is 6. That's not right. 6.
216.
26, yes. My mind got backwards for a second there. Oh, actually, it's written on my notes. I should just look there. 216. Instead of confusing myself up here. In general, we have calculators in our modern world, so we have a machine that does that. So we would just put each one of those digits in one of the columns and figure out what that is. So we have 3 216s plus 5 36s, 2 6s, and 1 1. And this marker is running out. Or this one will be darker. So when we add those up, what is that? 648 plus 150 plus 30, 180 plus 12 plus 1, 660.
841.
So that is the number as Americans we would think of with 841. I just kind of made that one up. I probably should have went with one that's in the notes that are in my hand. But there's nothing special about 10. All of our rules of math still apply. We can add, we can put 2 of those numbers together, add down the columns, represent any value we can make of. There's one rule of math that you probably haven't thought of if it was ever even told to you way back in elementary school, because it doesn't show up much in base 10. But when we stack the numbers into columns and add them like we do in elementary school, right? Like 34 plus 22, add and subtract or do any of that. And we add down the column, 4 plus 2 is 6, then 3 plus 2 is 5. Find the result of that. There is a rule that you may not have heard that we never want to add more numbers than our base. It doesn't really show up in base 10 because that means we don't want to add 11 numbers together. We don't want to add 15 numbers together, 20 numbers together at the same time. We don't want to pass 10. If we have 11 numbers we need to add together, we really want to add the first 10 of them together and then take the result of that and add that 11 numbers. Doesn't matter much with base 10. Base 6, we could still add quite a few numbers, but the one we're actually going for here, that rule becomes a big problem. Because the whole point of this is to get back to representing this, representing our 2 states. How can we do math with our binary states like this? Okay if I erase this one now? All these have been up here for a minute. And that little rule that that most of us probably never even heard in elementary school, because it's unlikely that we're going to try to add 10 or that we're going to try to add 15 numbers together by hand, suddenly becomes a big deal when we're in base 2, because that means we can't add 3 numbers together at the same Same thing still applies. We have a bunch of columns. 1, 2, 3, 4, 1, 2, 3. Yeah. Each one's a power of 2. Starting at 2 to the 0, which would be the 1, and then we double it. 1, 2, 4, 8, 16, 32, 64, 128. All the powers of 2, and just like in base 10, if we need a bigger number, we just add more columns going off to the left. We need a smaller number, we add columns to the right. We'll get to that in a second. And I'm going to make one up here. 1, 0, 0, 1, 0, 0, 1, 1. That sounds like a good number. So if you want to know what number that would represent, we'd do the same thing we did here. Figure out how many is in each column, multiply it by the power of that column, and then add those together, except it's a lot easier. There's another binary state, one that makes this situation a whole lot easier, is yes and no. So with our columns, we don't have to worry about there being 5 things in this column, or what's written over here, or 8 things in this column. It's a yes or no question. In this number, do we have any 128s here? Everybody see that? Does y'all on Zoom call? So yes, we have a 128. Plus, do we have any 64s? No. Well, we can just skip over it. Any of these? No. 16, yeah, looks like we have 16s plus 16. Don't have any 8s, don't have any 4s, and yes and yes. So changing the words we're using to represent that can be more useful for the given situation. Yes and no are often very, very useful things, much more useful than on and off. Like in this case, plus 4, oh, plus 2 plus 1. So what is that? 19, so 148 minus 1, 147. In base 10. So we can represent any of our numbers. We had a couple numbers and wanted to do math. All of the rules we know still apply. What did I do in these? There was one down in particular here. Oh, let me go right next. Let's take 16 plus 7. That'll work for both ways. We know how to do this in base 10, right? That's what we learned way back in elementary school. We got in the column 6 plus 7 is 13, and we carry a 1 to the next column. 1, and then 1 plus 1 gives us 2. Or if we use those same numbers to subtract 16 minus 7, 6 minus 7, 7's too big to take away from 6. So what we first learn is that we can borrow from this other column. We can borrow and then bring one of the things from the next column over, which is the next power of 10. So we're bringing 10 over, and then we get 16, 16 minus 7, and that's one we can do. We don't have anything left in the other column. So that, the adding up our column, carrying to the next one, or if it's too small, borrowing from the next column, we can do that no matter what base we're using. So these numbers, 16, we need 5 bits to write. Somebody want to tell me how to write 16 in binary? That's an easy one, right? Anybody in the Zoom call? We're just filling in columns, right? Just need to fill in columns until we get 16, so going through these are up here, yes or no question. 128 is too big, so no. 64 too big, no. Oh, well, 16 is right there. And we already found the number we're looking for, so we don't need anything else. And same thing with 7. We'll need a couple columns.
One zero one.
A little bit more than that. There's actually a little trick. I picked these numbers. This one is a power of 2, and this one's 1 less than a power of 2. So things that are 1 less than a power of 2 are going to be exactly the same as things that are 1 less than a power of 10. Like a million is a power of 10. It has 1 and a bunch of zeros. 1 less than a million is all 9s. We get the same thing in any base. Well, our base is always 1, 0, no matter what we're working at. Anything that's a power of that base is 1 followed by a bunch of zeros. And anything 1 less than that is the next symbol down. So we're 1 less than a power of 2, which was our 4th column. So we get all 1s in the first 3 columns. Because if we add 1 more to that, we would have a 1 in the next column. Then we can do the same math we did here. We need to add those numbers. It just kind of goes down the columns. Oh, I guess nothing's going to carry here then. 0 and 1 is 1. 0 plus 1 is 1. 0 plus 1, 1.
0.
Yeah. So that's the result of that. And if we check it, we get 16 plus 4 is 20. 22, 23. So our math checks out that way. Subtraction will work nicely here. So the same numbers, 1, 0, 0, 0 minus 0, 0, 1, 1, 1. So if 0 minus 1, that's kind of what we had written in the base 10 earlier, right? 7's too big to subtract from 6, so we need to borrow from the next column over. Well, we don't have anything, so we need to come all the way over here. And when we get over here, we can borrow from that, which leaves us 2 and 1, 0 in this column. And 1, 0 in binary is going to be 2, right? So 2 we can borrow from. So if we borrow 1 of those 2, we still have 1 left. Kind of like here, well, I guess that one went down to 0. 1, 0 is 2. So when we borrow 1, there's still 1 remaining. And same thing again, we'll still have 1 left. Still have 1 left. And eventually we'll get a 2 over in this column. But now we can take 2 minus 1. How much is that?
1.
Okay. And 1 minus 1.
0.
Again, 1 minus 1, 0. 1 minus 0 is easy. Still going to be 1. And we borrowed this one at the very beginning. 0 minus 0 is 0. So then we are left with a 1's column, 2, 4, 8. So we have an 8 plus a 1. So our math checks out. And that carry and borrow still works. Let me use numbers that carry better. I'll do 7 and 6. 6 plus 7. So 6 is, yeah, no 8s. Then we'll have a 4 and a 2. And 4 and 2 adds up to 6. And 7 would be 1 more than that. 7's already written there. 0 plus 1,
One.
1. 1 plus 1, or 2, but 0, and then we carry a 1 to the next column. And 1 plus 1 plus 1 is how many? Really easy one, right? 1 plus 1 plus 1
Plus one.
is 3. The 1, and we carry a 1 to the next column. 1 plus 0 plus 0, so then we end up with 8 plus 4 plus 1. Which should give us 13 again. So all the borrowing and carrying, and the main point there is that all the stuff we know from math, all the rules we know from math still work. Except for a slight issue. So we had to do a whole bunch of definition, a whole bunch of work to do the separate operations. Be nice if we could build all of it up from one single operation. So that's the next thing to look at, but it's probably a good time for a break before we talk about that part, right? 10 minutes sound good? Any feedback from the Zoom call? 10 minutes out, a 10-minute break sound good to y'all? All right, so my laptop says 7:14, so we'll get back to it at 7:24.